So today I would like to talk about Young-Lee zeros or the Young-Lee model. And this work actually is related to a recent paper I wrote together with Riccardo Bonsignore and Andrea Trombettoni in occasion the 17th birthday of John Cardy and a special issue of Journal Physics A. Now, what is about? We know that many physical quantity might show their deep nature just going to the complex plane. Now, the famous example is scattering amplitude, where Tullio Regge in 1959 showed that going to the complex plane, you can reveal the pole, and then from there, you know, there was a boom in high-energy physics with all the bootstrap program. So today I would like to talk instead of stat phys problem, and to show you which kind of richness you get just going to the complex plane. So let me just start with a couple of examples, very simple example, that probably will warm up the topics of the... So let's take just the natural number up to Q. And let's imagine that these are possible states of some fluctuating spin. Now, I would like to organize this in a different way. So I put there a kind of pentagram. And I also make thick of time, because I would like to follow how the spin change moving in time. OK? Now, at this point, I would like also to assign some weight to the elementary jump. Namely, imagine that I put a magnetic field, say, around one of these values. Let's say T. In this case, will be 2, 3, 4. I put a magnetic field along the 4 states. And then, once my spin jump at the time I to I plus 1, from A plus to A to B, I would like to assign a Boltzmann weight. Okay? So this Boltzmann weight is constructed in this way. Is as a z factor, z is a parameter, if the elementary path start from the point t, so it's a delta AT. And on the other hand, there is a b is the temperature, is weighted with a function phi AB of the initial and the ending point. What is this function? This is the coprimality matrix, something which we studied with Jacopo Viti and Giuliano Giudici some time ago, is an arithmetic function that just says 0 if these two numbers share some common divisor, otherwise it's 1. Now, all this information is encoded in a graph. So this graph says that there are some numbers which are friends of many, many others, while others are very isolated people. Now, at this point, I use this matrix. This is on a large scale. It's essentially a random matrix, is what we prove in our paper. However, as a very specific feature, if you go to Fourier transform, as a peak to all the inverse of the prime number. So you see this is half, 1/3, 1/5, 1/7, this and that. Now, this is the matrix I'm using to weight this path. And then I'm going to do a path integral on this space. Namely, I'm going to sum on all possible paths, however, weighted the trajectory according to the weight I just put it. So for instance, this path, if I assign a magnetic field along the 4 value, enter this sum with z cube. Okay? So at the end of the day, making this path integral, I get a polynomial. So this is another path that contributes, say, to z2 term. And so the question is, where are the zero of this polynomial? Now, let's imagine that we are in a very, very low temperature, and I take as a magnetic field one of the prime number. So when I do this, they become perfect circle. Okay? Now, if I increase temperature, the zeros start to move, but essentially remain kind of a C with some edges. Now, what about if I take instead a composite number? Like, imagine I take 6. Well, the zero are completely different nature. Now, I'm going to show you at the end of the lecture that there is a quantum device quotation, in which I can measure directly this zero in the complex plane using a decoherence process. So this implies that I can spot by pure physical experiments if I'm talking about prime number on composite number. Okay? Now, yeah. No, are completely real. No, I mean, there's Boltzmann weight. Look, the entire lecture is devoid to this. The entire lecture. No. Look, the entire lecture is devoid to this. You will see. Now, let me take another example, still on the prime, but cooked differently. So I take a polynomial, which I dub the prime polynomial, in which I construct a polynomial made of coefficients which are the prime numbers. And then I ask once again the same question. Where are the zeros, this polynomial? Can you guess? The zeros are like a globular star, like galaxy. Okay? So you see there are very distinct features according to what you are looking for. It's interesting to estimate this is a different story. I will tell you more. So, okay, so this is somehow to make the start of the seminar. I'm going to talk to you about the Young-Lee theory of phase transition, which is what is underlying this. I'm going to play with polynomial, in particular answer the question of Paul. I will talk to you about circle theorem and edge singularity. The Young-Lee model, which is the second part of my talk. You will see how recursive the story is, recursive conceptually. And then I'm going to focus the attention on partition function integrable quantum field theory, looking for the zero of these guys. And finally, I'm going to tell you how to experimentally measure these zeros in the complex plane. So imagine we take a gas with some fine extension of the molecule, and then we compute just the partition function of it, the grand canonical partition function, which is a polynomial of order n. Now, this is a real polynomial, as you said. So it's a real polynomial. In classical mechanics, it has a positive coefficient, but if you go to quantum mechanics, for fermions, it might have alternating sign. Now, being a real polynomial, the zero are either negative, all real negative number, or complex conjugate, because the polynomial is real. So, how to find this polynomial? How to find the roots? Now, Évariste Galois taught us in 1832 that you cannot solve a polynomial more than 5 degrees. So, how to do it? Well, you have to do numerically. And an efficient way of doing it, all these stories, you take this polynomial, you want to decompose in the root. What you do, you construct a matrices, and you diagonalize a matrices. Now, it looks a very masochistic way of doing, but diagonalize a matrices is much efficient way to spot the zeros. Because, for instance, you can apply many times. This select the highest eigenvalues, then you pick out this, and you repeat the story. So this is the most efficient way to get precise zeros of these things. Now, playing with polynomial, since I'm going to deal with generic polynomials, so kind of statistical environment, let me introduce some statistical quantity, which are the moments, as you do in statistics. So the moments are the roots, which I call ZL, to the power kappa. Now, all these quantities, of course, are related to the coefficient of this polynomial. Now, I'm going to show you that all the negative moments are related to the first coefficient, while all the positive to the higher coefficient. Sorry? Yeah, gamma 1, gamma 2, yeah. So this implies something remarkable, that imagine I start with a polynomial 1 plus 3z plus 4z squared and so on and so forth. I keep going. But once I fix the first polynomial, no matter how I increase the roots, the moments, which are spatial distribution of the root, has to remain the same. Once I stick to this as always the same. So for instance, this zero, the prime polynomial, no matter how I increase the degrees of this polynomial, the picture starts to become extremely complicated. But if I start looking, the moments are always the same. So the reason is very simple. So this is the, how to say, the experimental result of it. No matter how you increase the degrees of polynomial, these guys are constant. Now let me show you how you prove it, because I'm going to use it later and give us a very deep intuition of what is called cluster expansion in statistical mechanics. So I take the partition function, I take the log of this, I expand the log, and then once you do this kind of stuff, this is what you call cluster expansion in statistical mechanics. But then the interpretation is that these BM are nothing else than the inverse of the moment, are the negative moments of the roots, okay? So that being said, obviously the cluster expansion related to the previous polynomial in this way. So B1 is gamma 1, B2 is gamma 2 and gamma 1, and so on and so forth. So increase in this way. So this means that the first coefficient of the polynomial determine up to the third moments of the roots. And the other is done correspondingly. Now, another thing which is pretty interesting is if I give you a polynomial, where are the roots? Can you place where are the roots? Well, there is a very nice bounds. There are many literature. And for positive polynomial, there is a very rule of thumb, which is incredibly efficient. You just do the sequence of successive coefficients, and the minimum of these sequences is the lower radius of the annulus where there are the roots, while the maximum is the maximum of these things. So this essentially tells you immediately where to look for this zero in the complex plane. So for example, you can play around with this, with many of these polynomial, and start to see where the roots are. So you take some polynomial, you start playing with this, take another polynomial, start playing with this, take another one, start playing with this, and so on and so forth. Now the question is, can any distribution of complex conjugate zero, which are the only property I've been using so far, these distributions are real, so speculating with respect, can play the role of defining a possible statistical physics system? Well, to answer this question, we have to ask the master. So let me go to Yang and Lee, that were the first that looked at StatMech from this point of view in two very influential papers. So let me tell you what they found, which is the root of our understanding. So once you have these zeros, what they say is that you can define the pressure of the gas and the density of the gas. And these are completely determined in terms of the roots of your polynomial. Now, what they prove is that this function has a very specific properties. So in particular, in the region of the complex plane, which is empty of roots, the pressure is a continuous function, exists the limit v goes to infinity, is increasing function, positive, as well as the density of the gas. Now, being a positive polynomial can never have a zero which are positive roots. So the only way you can do if there is an accumulation of roots that finally pinch the real axis. When it happens, then you partition the plane in different regions, and essentially you have a different analytic function, the two regions, in which the pressure has to be continuous, but the density can be discontinuous, and this is the onset of the phase transition, and depending on the density of the zeros, you can have first order, second order, and this and that. There is a full classification of that. Now, that being said, so let me imagine that the zero condensate in an area on a curve of the complex plane, so that I have a positive density eta, and No, Z is just a fugacity. It's exponential of the chemical potential. Yeah, it's just how you rule the number of particles. Yeah. So with this density of 0, you can define the pressure in the entire complex plane in this way. And being a complex function, you divide real and imaginary part. And the real part is determined by the modulus of log. But the modulus of log, we know, is the green function of two-dimensional electrostatic. So this means that this satisfies this density of roots, the Laplacian and the Poisson equations. And in particular, when it's 0, it's to be an harmonic function. So this seems that you have a weapon to generate enormous number of statistical mechanics, just look harmonic function. So I don't know, you take our favorite example of this condensator, you take another one and this and that, you generate infinite number of things. The point is, but is it really true that any positive charge distribution electrostatic is good for stat phys interpretation? The answer, unfortunately, is not. Easy counterexample, I generate this random set of zeros, I compute the pressure, turns out this crazy function, I compute the density, is negative, so this cannot be any physical system at all. So this poses a very interesting problem, which is try to find which are the distribution of zeros in the complex plane, which might lead to new physical model. I want to say that there is a golden mine there. So we know how to define statistical models starting from the Hamiltonian. I'm proposing, give me the rule to rule out what are the distribution of zero which might lead to new physical system. And as a matter of fact, I do not know the answer in general, but I can show you that if the roots are on a circle, I know how to identify those distributions which give rise to good statistical physics model, please. Yeah, sure. It's nothing else. Yeah. Yeah, indeed. As only positive charge. Yeah, this is the problem. This is the problem. Indeed. Yeah. So let me now turn to the circle. So what I want to say is that in general, these roots can be anywhere as a crazy distribution I showed you at the very beginning. It can be this and that and so on and so forth. But now let me turn to a specific example, which actually is what boosted the entire subject. That was done by Young Lee themselves. So they prove a stunning theorem. I think at that time, people were really without breath. So what they say is take a easy model, generic easy model, on a generic lattice, ferromagnetic though. And then, when they took this lattice, they want to compute, given the Hamiltonian in presence of magnetic field, they want to compute the partition function. Now, this partition function is once again a polynomial in the variable which is the exponential of the magnetic field. And what are the coefficients? Is exactly like the coprime model I was telling you. Is the sum of all possible configuration given that the total magnetization is n. So is essentially summing on all possible underlying configuration which stick to the same magnetization. Now this polynomial is very peculiar. It's palindrome. You can prove it that n and m and n minus m is exactly the same. This goes with the physics of the model because putting a magnetic field up or down is the same. And what they show is that under this condition, the zeros are on a circle, okay? In general, you have this crazy polynomial, you look this coefficient, you cannot make sense of them, but if you compute the zeros, they are on a circle. However, if a circle, like the coprime model I was showing you before, for T bigger than critical temperature, they are on a C. And I have some age that will play a very important role soon. But when I start moving temperature, the zeros start to move. And then for T less than Tc, they cover uniformly the circle. Okay? So what are the general features of this distribution? Well, first of all, this pattern emerges only if you have ferromagnetic coupling. If you have antiferromagnetic coupling, start to be on the real axis negative. If you have spin glasses, start to be crazy in the complex plane. The spreading of the zeros, you can immediately understood it just due to interaction. Because if you start with any system, non-interaction, there is only one root, which is there. You start putting some interaction, they start to split, put more interaction, start to split, and split, 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 split. So the fact that they cover the circle is as much as all these spin are interacting each other. Now, I want to stress that the only known analytic distribution, the only known, is for 1D Ising model. There are no other model in which you know how they are distributed, these zeros. And the distribution is pretty simple. It's given by this law. And I would like to stress that if you knew this density of zeros, you can get something stunning in statistical physics. Alias, you can compute the magnetization of Ising model, in this case, in presence of temperature and magnetic field. A problem that not even C and Young was able to solve and remained there, and not even Baxter were able to solve, okay? So this is the formula. So if you were able to get this, say, for two-dimensional model, you will get really the equation of states in analytic form. So the fact that nobody succeeded as tell you what are the difficulties here. Now, I will take this example to show you what I claimed before. What I claimed before was, can I, given a set of zero, define an honest statistical mechanism model? I want to reverse the logic. I told you that in general, I'm unable to assign this zero is good for. But if I knew that they are on a circle, I can do it. It's enough that this function, which is the density of zero, is as the positive derivative. Any of them can play the role. And the reason is I can do change of variable in all the various formula and show that if this function has positive derivative, the corresponding density is positive, the pressure is positive, it's increasing, it satisfies all the things I knew it. This is a golden mine. I can take any function which is increased positive and define new statistical model, okay? Whose property has to be seen, of course. Now, let me now go to what are these Yang-Lee model. My talk was Yang-Lee zero and Yang-Lee model. What is the Yang-Lee model? Well, you have to go and concern with the distribution of the zeros nearby this edge singularity. Now, what people discover is this problem is interesting itself. Because if you go and look what are the density of zeros nearby these edges, is anomalous, dictated by a critical exponents. Now, it was essentially Griffith, Kortman and Griffith, that realized that for all purposes, this anomalous behavior is nothing else than one among the other critical phenomena. But if it is so, there should exist a field theory, Landau-Ginzburg, that describes it. Okay? And this Landau-Ginzburg was found by Fisher and called Yang-Lee model. Probably should have been called Fisher model, because he did it completely, but he named Yang-Lee model. And what is about? The Landau-Ginzburg, but very crazy one, is phi cube. Phi cube, if the coefficient is real, is unstable. There is no ground state. But this Lagrangian has imaginary coupling. So such a field theory is not Hermitian. However, is CP invariant. CP invariant means that I can make a transformation on the field, which changes the sign, such that the action under this conjugation map into each other. Now, this property is enough to ensure that the spectrum of this theory is real. If the theory is Hermitian, we know it's sufficient, but it's not necessary. You can have a real spectrum with a theory which is not Hermitian, but is CP invariant. And this field theory, as it is, has an upper critical dimension, which is 6. So there is, as a matter of fact, a solution in lower dimension, in d equal 2. So at criticality, this is described by the simplest conformal field theory. This was found by John Card in 85. So it's a model based on two fields, identity and relevant fields, of negative dimension, and fusion rule, which is the simplest as possible, with central charge minus 22 over 5. Now, this theory also is solvable away from criticality and give rise to the simplest integrable field theory. Now, I have to describe you in short what the integrable field theory is. Means that in addition to Noether current, you have infinitely many other current of higher spin, which are conserved, and these charges commute with the Hamiltonian. And when they act on a bunch of particles, they are just proportional to the higher power of the momenta. So this means that any motion has to be ruled by an infinite number of conservation laws like this, and therefore, no surprises, highly constrained. So indeed, in a field theory, usually you have a process, production process, but in presence of these charges, you have just elastic process. Yeah. Can be, yeah. Can be, yeah. So this integrable model, in a way, is a very interacting model, but in a way, the most harmonic one you can think of, okay? So it does many, many things, but in a very, very elegant way. And in particular, it satisfies the so-called factorization process, which allow you to concentrate the attention at the level of S matrix just on the two-body S matrix. In general, in field theory, the problem of S matrix is astronomically complicated. But in this model, you are allowed to focus the attention on two-dimensional, on two-body scattering matrices, because all the rest will be just getting by factorization. Now, this S matrix has to satisfy very simple conditions, which are unitarity related to the S channel, how it's called in high energy physics, to the crossing symmetric channel, which is the T channel. So it has to satisfy two functional equations, which are very simple, like this. And we found this S matrix with John. Okay? This is the exact S matrix of the Young-Lee model of Fisher. So satisfy all these equations, but on top of that, has all the right ingredients to match this Lagrangian. For instance, the Lagrangian is phi cube interaction. So it means it should have a bound state in which the particle is bound state of itself, because it's phi, phi, phi. Indeed, you see this S matrix as a pole, and when you go to the pole, you realize that you are discussing exactly the same particle enter the asymptotic states, and moreover, what is important is that the residue, which in general in an S matrix has to be positive, in this case is negative. Why is negative? Because the coupling was imagined themselves. Take the square, has to be negative. Okay. Okay. So this is about. So at this point, I'm showing you Young-Lee zeros, which concern with pattern of zero statistical models. I've been defined for you a particular integrable model which describes the age of these zeros. And so I pose really the problem I was curious about. So I would like to compute and study the pattern of Young-Lee zero in an integrable model. A Young-Lee model is one among many others. It's a prototype. So in a joke, it's kind of Young-Lee square problem. So I'm looking for the zeros of a model which is defined by the zeros and so forth. But it's not absolutely particular. It's completely generic, the story. So how to do it? Well, for integrable model, as a matter of fact, we know the free energy. The free energy is given by a very net expression, which remain under all purposes the free expression. With a caveat. The caveat is, in a free theory, that would be just the energy of the one particle states. But for integrable model, this function which is there satisfy a non-linear integral equation which take care of all the interaction of other particles simultaneously. So say differently, in integrable model, all particles to be happier in their own way, in presence of all the other, not isolated. Free theory, each one stays for his own. Here you have to find many body problems at the same time. So at this point, what you have to do is to solve this equation and realizing where these zeros are, nothing else. So we have essentially to find the solution of this equation and see where the. So I think that all we agree that the most integrable model is the free theory. So let's look the pattern of zero free theory, which is already interesting. So you have the free theory partition function you develop. This is the polylogarithmic function. I expand, I compute the zeros of this polynomial. Here they are. So they looks to be on a circle, but the devil is in the detail. They are not on a circle. This limiting curve is all but circle. So the easiest way to show is that you compute numerically the radius versus the angle, and you see it's not a constant. But I have a very cute proof of this. The cute is, you remember that I have the cluster expansion of this. The cluster expansion was related to the inverse of the zeros. If they are on a circle, since they are complex conjugate each other, this is the cosine and theta. So this coefficient has to be the Fourier coefficient of the distribution I'm looking for. And therefore, I should be able to compute this distribution according to the Fourier function. But I know to sum this series, many, many cases. I just show you a couple of examples. So imagine I take this, which I think is related to three-dimensional system. I know what the sum is. I can take another one, I know how to sum it. And when I plot it, the Fourier sum is negative in some interval. This means cannot be. Cannot be. This limiting curve is not a circle. It's something else. So although it looks a circle, it's not a circle. Okay? Okay, so that means say, where are the zero Young-Lee? Well, so this you have to solve this Bethe-Ansatz equation, and you do it in threefold way. You first find solution for epsilon, you plug in the free energy, you expand the partition function. So for expanding the energy, you put a series in Zn, you plug in, and you get hierarchy of equation that you solve numerically. Once you got it, you go to the free energy, you expand it, you plot it, boom, 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 boom. You get all these coefficients this way. And finally, you go to the partition function and got the polynomial. So to make the story short, here are the zeros for various value of the temperature. So they are essentially on a circle with the same caveat as before. They are not circle. They are almost circle, but they are not, strictly speaking, a circle. Nevertheless, there is a beautiful law which rule the radius of this circle by temperature, which is this. And this law is very, very nice to understand the origin, because this is how you spot numerically, because if you go to very large B, alias low temperature, the system reduced to free theory. But free theory is Bessel function. Bessel function asymptotically is exponential. But once I have this polynomial, I told you the bounds before. So given the exponential behavior of the coefficient, I know immediately how the zeros should behave. Where are the circle, the annulus? And F2 is match between two exponential that type. More interesting what happened to small b, because when you go and develop the solution of Bethe-Ansatz equation, the solution starts to flatten and become flatter and flatter, order 1 over beta. So the function is constant 1 over beta. So this is enough to say that the partition function is to be 1 over beta time a universal function which I can compute in terms of the fugacity. So once again, I apply the bound, and the zero should vanish in this way. Okay? Okay, now the last part of the story, how I experimentally measure this guy. Now this proposal is an amazing proposal by Bobo Wei and realized by Peng. And the story is like this. You take, let me illustrate for Ising that is very familiar system. You take the Ising model, classical. You can do also quantum, but let me do classical. You take the Hamiltonian like this, and you take a quantum spin that you make it couple to all of them. Okay? So this add a new term to your Hamiltonian. So this is the quantum spin, and this is the classic one. And this spin, of course, can fluctuate it. Can be plus and negative. But each time that it fluctuates it, induce an Hamiltonian on the spin buff. Okay? So the spin see either a magnetic field up or magnetic field down. So at this point, what you do is you take as initial state of the spin a linear superposition, plus and minus, times tensor product of the environment. And then, when you do the time evolution of these states, the plus evolve with H plus, and the minus evolve with H minus. So I give you interference. So in particular, if you go and measure the expectation value of the transfer spin, you find is ruled exactly by the difference of this Hamiltonian. But the difference of Hamiltonian is just the quantum spin I just gave you. So if my environment is thermal, I have to trace on this. But tracing on this is just the Young-Lee zeros. In this case, just shift it appropriately by this term, which is the time evolution. So this is the expression. And therefore, if you measure the decoherence of this spin, so for instance, I took a system of 10 spin. This is the decoherence function. And you see, this function has zeros exactly where there are the Young-Lee zeros in the complex plane. Okay? This is just the time evolution of this spin. And this function has zeros exactly where are the location in I theta. So these are just theta. Because you know that zeros are exponential I theta. Okay? Now let me take you another example. This is what is about with n equals 16, temperature beta equal 8. And find zeros exactly where the Young-Lee zeros are. Okay? So you just do measurement of decoherence and you spot where is zeros. Now these things is not fanta science. People have done this experiment. Peng have done these experiments. So how he does? Well, you know, experimentalists, you have to be a bit kind with them. So he used this molecular of, which involve phosphorus. So this is a big atom in center is phosphorus, connected to carbon and hydrogen. So for him, the 9 hydrogen is the thermodynamic limit. So is the probe, the internal spin is the quantum probe, which is phosphorus with a spin that can be tuned in 2 states, coupled to 9 classical spin that thermalize to it. So he can tune this and has done the experiments. He has done. And so he just plot this decoherence and were able indeed to spot the zeros of these things. Okay. Okay, conclusion, I just go to the